Hello, everyone. Good morning, good evening, good afternoon, whatever is appropriate to where you are. Thank you so much for joining me here. I can't tell you what an honor it is to be asked to speak to all of you and to share a few thoughts that I have about machine learning, where we are, where it is perhaps we could be going. Before I dive into that, I think it helps to take a little bit of time to give you some context, to tell you a little bit about my beliefs, what it is driving the kind of research that I do and what this talk is really about. And it's really a simple thing. It's that the field of computing, and machine learning in particular, has exploded onto the world stage. We're central to everything that everyone does, and the problems we work on genuinely matter. And they matter not just in the way that they teach us something about the world, but that the products of our work, be it research or engineering from industry or from universities, they're out there in the world and having a dramatic impact on real human lives. Now, it turns out this puts our work at risk, and it requires us to take a certain level of responsibility in the way that we do that work. But while this is true, it's not necessarily helpful. It doesn't tell us what to do or who needs to do it. And also, it doesn't help us to think through the pros and the cons, the trade-offs of different courses of actions. So what I want to talk about today is a way of thinking about this new world that we find ourselves in, and to think through the consequences of really adopting that way of thinking. So my conceit here is simple. There's an underlying claim, and that claim in the main is that as a community, we're compiler hackers. And that what we need to do is we need to spend at least as much time being software engineers and programming language nerds, and maybe ethnographers. More importantly here, software engineering, programming languages, ethnography probably doesn't mean what you think it does. And I've got good news and I've got bad news. The bad news is that this is a lot more work than we probably want it to be. But the good news is we will do better science, we'll do better engineering, and the world and the field will be better off for it. And that's the argument. But that argument makes some strong claims and needs some evidence. So to that end, I want to spend some time providing some context of how other fields work compared to machine learning, show some examples of problems, both social and technical, that arise because of our current approach, and then outline how we can address these problems methodologically, and show that that will open up some really interesting technical questions and some really important social ones. Now, it turns out that if I reflect on it, that the arc of my own work mirrors this structure rather nicely in some ways. But I've been quite focused on a smaller set of problems and solutions than all the ones that are out there. So if I just sit here and I talk about my own work, well, I drown in irony. Luckily, we live in an age of magic. Sometimes that's a good thing, sometimes that's a bad thing. But it means that I can show you more than just my own work, bring in a wider set of voices, some of whom see the world the way I do, some of whom do not. So let's do that. But first, pardon me while I get into character.
73, 74, 75, 76, 70. What is that? Hello? Who's there?
It is I, your office mate from your days at AT&T Labs so many, many years ago.
Charles? What are you doing here? And wait, we weren't office mates. You had your own office. You just hung out in my office a lot when you were bored. Kind of like this, actually.
Well, I was bored a lot, so we were office mates. Anyway, I came here tonight because I'm worried about you.
Worried? How so? Life is great. I mean, I was just here counting my NeurIPS citations. Things are pretty good. I mean, have you seen my H-index?
Yes, Michael, I can see it from space, but I don't think you should be dwelling on that. It's Christmas Eve, after all.
Christmas Eve? No, that's later this month. Also, you know I'm Jewish, right?
Whatever. This is exactly why I'm here, Michael. I don't think you're paying enough attention to machine learning and what it's doing to the world around you.
No, I'm paying attention to it. It's awesome. I've never had so many people interested in taking my classes, reading my research, asking my opinions on things. It's been really great. For me.
Yes, Michael, for you. But there's a bigger picture here, and you aren't seeing it. My job here tonight is to help you to see it. And hopefully, you'll see not only that there is a larger world that isn't doing as well as you are, but that maybe you aren't doing as well as you thought. So tonight, what I'm going to do is I'm going to introduce you to three sets of people. Some will represent computing and machine learning research past, some machine learning research present, and others machine learning research yet to come. And they have important information for you.
Hold on, hold on. Is this some kind of Christmas Carol themed keynote? Is that why I'm wearing this weird hat? Wait, you cast me as Scrooge?
Well, I mean, you're certainly old enough to be Scrooge. But the important thing is that I want to talk with you about machine learning and algorithmic bias and how we can fix it.
Algorithmic bias. You mean that made up idea that says math likes some people and hates other people? I can't see how there's anything to fix. But look, man, it's your almost but not yet Christmas to waste.
Wait, you don't believe in algorithmic bias? You don't think machine learning can be biased against certain people? If a machine learning algorithm recommends a man over a more qualified woman for a job, is that not biased to you?
I mean, I'm willing to believe that you can feed a machine learning algorithm bad data and it will make biased decisions, sure. But it's the data that's the problem, not the algorithm. You want a better face recognition system? Get better image data. I can't help you with that. It's not a machine learning research problem. It's an implementation issue. Look, I'm not saying it's not important to get it right. I'm saying it's not my problem.
Oh, so bah humbug.
No, that's not it. Not humbug. I'm saying it's not a bug at all.
Oh, so then it's a feature.
Well, yeah, it's the features provided by physics.
Michael. You know, those who cannot remember the past.
I know. We're condemned to reinvent it. And that's exactly what we're doing. We're just trying to make things better.
Maybe voices from machine learning research past can give you some insight. Let's start with your ideas about physics.
So the camera, in essence, is a sensor that's capturing light from the environment. And one of the foundational things we learn in computer vision from day one is image formation. That is how light is going through optics and then registering on a surface, which is where it could be captured. That's physics. Then you start removing the pinhole and make it into a lens. Then it does various types of things. Then the amount of the size of the aperture, the amount of the physical light that's going through that pinhole to a lens, to a surface, all of that are different types of things that you can actually now impact. I can, on the optics, make it be a little bit of a red tint lens. That's going to filter out some of the light sources, and that's going to make different types of background images. Those are choices that photographers can do. Now, one of the biggest choices in the old days was, what kind of film I'm using, black and white or color. And that was a choice that, a photographer would make, or sometimes even a camera manufacturer would make in terms of what optics they're putting in, or the film manufacturer would make on what kind of film they're making that I would buy to put in there. So each one of them would add a different set of variations on what the outcome would be. The filmmaker, companies like Kodak and Fujifilm and stuff like that, spend a lot of time on trying to give us the best possible chemical solution to give us a print. And they optimized over lots of different criteria. It would always end up with a darker image of non-white people. But even in speech, the microphones and the speakers that were being built in the early days were not very good at capturing the tonality that was different between males and females.
So you see, even physics isn't just physics.
Oh, it's unjust physics. Come on.
Look, Michael, the reality is there are dozens and dozens of decisions that impact the image the camera gives you or the recording that the microphone gives you. And each of these decisions might be justified in terms of making a trade-off, but they're trade-offs nonetheless. And the thing about trade-offs is that they make some things better and some things worse.
So the pixels in the images I train my algorithms on are my problem now?
Well, yes, in the sense that dealing with what they lead to is your problem. And it turns out it's something you can do something about. Listen,
I do human-robot interaction, healthcare. I work primarily with children with special needs. And part of that is that we design emotion recognition algorithms to recognize the emotion of the kids, to make sure that they're engaged. Maybe they're frustrated at the therapy, at their intervention. And so we really look at emotion recognition. Our outcome was that in the intervention, which is basically robots getting kids to exercise, the boys improved at a better rate in terms of motor outcomes than the girls. Now, the girls did improve, right? So it was not that it was like, oh, this is like horrible, but there was a difference. And the way we fixed it was we designed a specialized learner that would recognize, we would recognize when we had an anomaly. And the way we recognized this was that if our system was consistently wrong for a certain parameter, it means that our system screwed up somewhere, right? It's not that these are anomalies, it's that our system screwed up. And can we get our system to recognize that and then design a specialized learner that then took into account and expanded on what we've already learned? The boys' recognition accuracy stayed the same, but the recognition for the smaller group, the girls in this case, improved.
So there you go. That's an intervention where our systems have to deal with different groups of people differently. And if we're aware of that, we can actually perform better, not just overall, but with all of the subgroups. Now, here's another example of natural language processing, where one of the challenges is what kinds of unintentional patterns exist in the training data.
And so the argument is that connectionist networks learn mere association, statistical combinations of those inputs, and so they can't be doing this kind of higher level reasoning stuff. And from that perspective, I think I came into this very much a skeptic because I came out of a kind of more traditional linguistics training at University of Pennsylvania. They have a really kind of interdisciplinary type of NLP group. And linguists are predisposed to like to believe in structures and abstractions. And so there's a lot of skepticism around these kinds of statistical associations. A lot of the things I expected them to do badly, they don't seem to be doing as badly as we would expect. But we do have decent evidence that like generalizing across the kind of raw perceptual inputs, the individual words, you can reliably say like, yes, it's detected that these are nouns and those are verbs, and it seems to differentiate those and generalize to held out data and things like that.
Ha! See? Machine learning algorithms can even solve symbolic tasks.
Can they?
So I think that a lot of the times these models are picking up on these kind of artifacts of the training set that lead to good performance on that training set, and they don't generalize out of distribution. This doesn't seem like a particularly, it's like gotten so much attention, but at the same time, it's really not surprising to like any of us, right? It's like why wouldn't the model exploit this? So in the natural language inference case, it's like, yeah, 80 to 90% of the time that the word not appeared, the model, the correct label is contradiction. So that's a really solid signal. The model has no way of knowing that. That doesn't generalize it. This training data is its whole world. How do I make my model work better on the real world? And you say, make your training data look more like the real world. That seems like a fine solution, like in kind of a practical setting, right? But as a kind of scientific problem, as a way of getting models to be more robust and generalizable, I don't see data augmentation as a solution. It just seems like you just defined the problem as a non-existent problem and then said that you solved it.
What I hear from Ayana and Ellie is that we have machine learning techniques for improving the accuracy of machine learning algorithms, specialized learning, using data augmentation to make the data reflect the task better. That just means we have license to focus on what's really important, machine learning algorithms.
Well, maybe that's what you hear, but let me tell you what I hear. What I hear is that in both cases, you have to really take the time to understand your data and where it's coming from, as well as thinking hard about how your model is going to be used in the real world. We cannot sidestep this need. We have to embrace it. In computing, there's a whole field that worries about these things, and it's called software engineering.
I don't care about software engineering. That's merely coding, and I code in a high-level language called Graduate Student.
Okay, so this is a great question because software engineering and coding very often are kind of incorrectly conflated. And so people tend to think that, if you're a software engineer, it means that you can write code. And that's actually not the case. So that if you want the official definition, typically the way in which we define software engineering is the systematic application of methods, principles, and techniques to build software in a rigorous way. I think people realize the importance of software engineering by doing it. Thinking about the consequences of what you do, what you build, and how you build software systems is fundamental. And it's a hard thing to do because in many cases, especially, you got a task, you got pressure, and you want to get that done. But it's something that is very important, and people should do. And I feel like software engineering gives you the framework to sort of facilitate this sort of considerations, to facilitate this process of taking into account possible consequences of technical and non-technical decisions. And more generally, apply more rigorous approaches to system development for any system that is not a toy system, for any system that will go eventually in the real world.
I mean, obviously, I'm in favor of rigor, but it seems like you're asking me to do a job that I'm not really trained for. I like the idea that I could just hack up whatever I want, and then the software engineers can pick up these ideas and make them ready for prime time. I mean, it's not like research code gets out into the real world and causes harm or distress.
Okay, look, well, maybe that was true in the distant past, like when you were first old enough to pick up Social Security. But now, the pathway from research code to broad dissemination has sped up orders of magnitude. Let's leave the past and hear some tales from machine learning research present.
Are you going to tell me something non-obvious?
So I think the obvious case is law enforcement, but I think in areas ranging from predictive hiring. Across the board, I think we can see there's a lot of very near-term or currently happening negative applications of predictive algorithms.
Okay, I walked into that. So what next? You're going to talk about that dust-up on Twitter that shook you up over the summer? What was it called again?
Wait a minute, are you trying to say got me shook? You're so old. Look, the system you're thinking about that created high-resolution faces from low-resolution input is called Pulse. And it's built on top of a face generation system called StyleGAN.
So taking the example of Pulse, I observed that a lot of the focus of the conversation was how it took people of color and when it upsampled their images, turned them into white people, but just not white people, but white people that didn't look anything like the originals, except for maybe kind of broad shapes. And that wasn't actually what stood out to me. What stood out to me was how people like Obama and myself, who are of mixed race, other people who are more ethnically mixed in their background, like AOC, how it would take their people, it would when it upsampled our images, it showed new images that looked, new people, generated people that looked a lot like the originals, except that it had removed all of the nuances that we would use to distinguish these people as people of color.
Okay, so we actually have tried to fix, some of the problems with StyleGAN using new algorithms, but it actually doesn't work very well because of the way StyleGAN, because of StyleGAN. The people with kind of African features are kind of spread apart in latent space, so it's actually really difficult to request a certain an image with certain types of facial features. But like I said, that's not something that we had built into the algorithm before, right? Or even now. If you want the machine learning algorithm to do something, you have to ask it to do that.
And these kind of problems are going to keep on happening because the world has fundamentally changed.
But I guess my own view of it is that, especially when I compare the way machine learning was when I first became interested in it and now, I think, a huge watershed moment was the advent of the consumer internet. So, back in the day, the main application areas for machine learning were often to predicting, systems level or collective types of behavior, directional movements of markets or predicting weather patterns or things like this. And once we all started generating huge amounts of data on our own activities and interests, it became possible to apply, predictive modeling at the individual level to make predictions about particular people and what they were going to do. And I think once that happened, as I said before, this kind of caused machine learning to bump up against society at large and started to result in a lot of the kind of things that we've heard quite a bit about in the news, especially in the last 5 years or so, about machine learning resulting in discriminatory models, in models that are opaque, in models that leak privacy and the like.
I open up my iPhone, and you know how iPhones have this feature where they can kind of quickly recognize faces in your photo library. My phone routinely confuses me from my other dark-skinned friends. Even just in basic experiences, kind of navigating and testing things out, I realized that I kind of wasn't in mind when these things were being built and designed. And so that's kind of just my firsthand experience with observing and seeing the bias in a real sense.
So, Google tried to hit this right with is this a man or is this a woman? And, we're realizing that perhaps gender is more varied than that kind of question.
Like I said, I could talk about facial recognition all day because there's all kinds of concerns, like whose data is being used for facial recognition, for training facial recognition systems. Did they agree to have their data used for that purpose? And then, if we use these systems and they discriminate against people, well, is there some way to mitigate against that? Is there, if they flag people who are not correct, is there a human in the loop who can help mitigate the problem? Or are we going to arrest people just based on a match from a flawed facial recognition system? So there's all kinds of really interesting questions about facial recognition that, frankly, we should have been talking about years ago.
So in particular, one that frustrated me was when I don't remember the particular institution, but they had this computer vision model that couldn't correctly classify Black women, but it could classify other women who weren't Black. And the thing that it classified the Black woman as was particularly frustrating to me, and I won't repeat what it classified her as, but that was particularly frustrating to me.
I hear what you're saying, and I agree with you, but it's not fundamentally different from the stance that I started with. Yes, there are real problems, but they aren't our problems. I mean, they aren't problems that can be solved by machine learning researchers.
They aren't problems like what?
Like bias.
So I know that some people, ask this as a question of, is there actually bias in the math itself? And I would say, I can even sidestep that question and say it doesn't really matter to a certain extent because the way that we use algorithms can introduce bias. And I mean this in this technical bias sense, which could have implications for fairness as well.
And I think one of the additional things that builds upon this issue is that we have moved towards a regime of greater and greater parameterization of the problem. If you want to improve generalization, you end up needing more parameters. And so the general trend is more generalization is more parameters. But more parameters often then is associated with more data that needs to be fed to learn the model with the more parameters. And so as a result, we are in a regime in which we cannot generalize efficiently. If we're going to say that the algorithm is biased, we're going to say that the algorithm is biased towards requiring more data in order to generalize and requiring more parameters in order to generalize. And to me, that is a definite sign of bias and has downstream effects in terms of data collection.
Once you actually start having to build things like rewards and states and actions and all these things, we don't just get these environments for free, typically, if we're really trying to use them. We have to come up with these environments. And so this is another consideration that you typically need when you're going into things like industry and you want to use this.
A lot of the question of that people in language acquisition and linguistics and all of that work on humans, this is what we've been trying to understand forever, is what kind of inductive biases do humans have that allow them to generalize from the data they get?
machine learning feels like magic because you're taking all of these things as input, but you've done all of this work to get to this point where you could transform it into knowledge, right? So the machine learning, it feels like magic, but actually the whole setup of the magic trick is what really mattered there. Here we are doing parlor tricks, right? But the truth is that we could be out in the world solving the world's real problems with our technology. We have to be careful to realize that the sales pitch, the selling point is right now is the parlor trick. It's not the real world implications. And I truly think it would be better if it changed. You know, every aspect of what we do is biased by our background, right? There's no such thing as an unbiased human, right? We are all biased by the way we've been brought up. But there's something very important about the life cycle of the data science process that we're missing here, which is that if you find that the system has a kind of bias that is harmful to people, you should go and fix it.
While this doesn't solve the problem, it's important to admit the problem.
So then, I guess we agree. There's a bunch of kinds of bias. There's inductive bias, there's technical bias, there's personal bias, and so on. Bias is a problem, and it can creep in everywhere and anywhere in the pipeline.
So yes, I admit we have a problem, but that's not the same as solving the problem. Do we even have the tools to really deal with it?
Maybe. What if I could present you with irrefutable proof that we do?
Well, I'd be surprised. After all, you don't do theory.
Well, no, of course I don't. Theory is for the weak. But I do know someone who does do theory.
This is actually one of the topics on which kind of rigorous theoretical thinking is important because it's an area where getting definitions right, or at least good, is very, very important. So, you know, to say a little bit more about that, I think this audience will be, you know, very appreciative of the remark that, you know, even though theoretical computer science was reporting on how intractable various learning problems were even decades ago, astoundingly, that did not prevent the incredible empirical success that machine learning has experienced. And so I'm sympathetic to the view that, you know, you didn't need definitions of learning or theorems for the practice of machine learning to become very successful. But I think on these more social issues, where you're really thinking hard about it, what it means for an algorithm or a model to be fair or for it to be private, definitions matter. And I think the analogy I would draw is that it was very important in the kind of progress of public key cryptography to get the definitions right. You know, so there was, you know, depending on how you count, hundreds or thousands of years in which cryptography was essentially a game of whack-a-mole, where, you know, one person would propose an encryption scheme and somebody else would break it. And it wasn't until people got the definitions right in the 70s or so that it put cryptography on firm algorithmic foundations. And I think that kind of thinking and that type of theory is especially important in machine learning on these topics around social norms.
Okay, well, that was a kind of a low blow. Pretty unfair. First of all, he was our boss back at AT&T. I feel like I have to believe what he says, even if he's wrong.
Is he wrong?
It doesn't sound like he's wrong, but he could read me the phone book, and I'd believe it would run in polynomial time.
Wait, that doesn't make any sense.
I believe you're right. Anyway, he makes it sound important, worthwhile, and interesting to care about these problems.
But, I mean, there's always a but.
But...
Wait. Let's let Kearns tell us the but.
But I shouldn't be the one that, you know, looks at the curve expressing the trade-off between overall predictive accuracy and false imprisonment in a criminal justice application. I shouldn't be the one that points at that curve and says, okay, this is the right balance of overall predictive accuracy and false imprisonment, right? Hopefully, somebody who's thought much more deeply about criminal justice and knows the application domain and the data that's gathered and the consequences of the decisions much better than somebody like me should be making those decisions. But as a technical community, we need an interface to the community of people like that, okay? And it can't be, well, go get a PhD in computer science and then we can talk.
It almost sounds like he's talking about accessible programming languages, but no programming language person would think this makes any sense for machine learning.
No programming language person?
And I think many programming language people will call themselves, PL people, in the sense that when we look at, even computations, or when we look at, let's say, even just the world, we're thinking of ways of how do we distill that into little computational objects that work together, and what are the interfaces between them, and how can we get those interfaces to work together nicely to get a system that at the end of the day satisfies some particular property. For me, myself, and even before systems like TensorFlow and PyTorch had really been released or even were made available, certainly in the way that they are now. But looking at these systems, it was very clear to me that there was a community of people who were building very interesting artifacts and starting to ask very interesting questions about how they should compose these systems. And not only to get them to work, right? Can we get state-of-the-art accuracy on X, but even more increasingly over time, how do we make them interpretable? How do we make them robust? How do we think about generalization? And these are all the types of questions that I'd like to think about in systems, for any system. In the machine learning community, what's so interesting is I don't know if these abstractions exist yet, right? And so, while one might like to, whip on the machine learning community for building these systems that they don't understand, I think that's the promise of the science at this point, is we don't understand what these primitive abstractions should be, and that's the research pursuit. So data, just that input-output relation that we may have from, let's say, supervised data, that is one part of the specification where we care quite certainly about accuracy. But that's not the complete specification, particularly when we're talking about bias, right? Where I think many systems people would say if your specification is incomplete, then you can't expect your system to satisfy the full specification.
And there's your programming language person.
Touche. Say, have we moved on to the future now?
Yes, kind of, but we're also still in the past. You remember that work we did way back in 2015? We did all this effort to try to work on programming languages for reinforcement learning. Now, why did we do that? Why did we care?
Well, because we wanted to find a way to define reward functions that really got to the underlying tasks, not just something that would generate the policy we wanted in one specific environment.
Exactly. And we wanted it to be accessible to non-machine learning experts, right? Right. Okay, back to the future.
Wait. You can't have Kern showing up in both the present and the future. That breaks the analogy with A Christmas Carol.
Okay, look. First off, you know that Kearns is eternal. Second, stop breaking the fourth wall.
Fine, but they know that you're wrong.
So anyway, as I was saying, we need accessibility for non-machine learning experts, especially when our machines are making decisions for others.
And in high-stakes decisions, really bad things can happen to people when the models are not transparent. Like, you could end up in prison for extra years. I mean, this is not the way the criminal justice system is supposed to work, right? It's not supposed to decide a typographical error in someone's complicated black box model. That's not supposed to decide your prison sentence. That's just not how it's supposed to work. And then also with medical decisions, if you don't have a human in the loop, medical decision making can be very dangerous. And things like loan decisions, right? If your loan gets denied, you might not be able to start that business that your whole life and your career really depends on, or you might not be able to buy a house, right? I've worked on a lot of different applications, from energy grid reliability to healthcare to criminal justice to, you name it. I've worked on it. Computer vision. And I have never found a case where we could not construct an interpretable machine learning model that was just as accurate as the black box counterpart that we were comparing with.
So, would you argue that if we applied our computational specification thinking, we would be able to bring more folks along? And this would somehow help us identify bias and stuff?
Yes, exactly. Look, computational thinking teaches us how to specify what we want precisely. Now, machine learning allows us to relax that a little bit so we don't have to be perfect in our specifications. Instead, we can let the machine learn and fill in the gaps. Now, just because we can do that doesn't mean that we can abdicate our responsibility for making certain that our algorithms learn what they're supposed to. In fact, it is both a scientific and ethical imperative.
But the idea is that you use, a program to specify much of the structure of the task that you have at hand, right? And then you leave some holes. So it's kind of like a sketch, right? And in those holes, what you hope is you can use the data to complete those holes. Right? And I think the way that many programming languages people or people who are working in between these boundaries see it is that what we'd like to be able to do is take that sketch. Then you could perhaps reason about bias or several types of properties just using that sketch. And then you hope that any completion of the rest of that program using the data will still satisfy those properties, will still preserve that specification.
Okay, so let's take a moment to take stock. So far, we've seen that we haven't always treated the machine learning problem as a systems problem. But if we do, we know we have to make these systems accessible. But there's even more. We have to make sure all the people are in the room and that we understand that they are domain experts and they are folks who genuinely care about machine learning and genuinely are machine learning researchers.
I think that diversity is actually tremendously important, and having the right people in the room when decisions are made. And I've changed my mind about that a little bit recently. When I first started working this area and realized, the reason discrimination creeps into our models and algorithms isn't because of racist or sexist scientists or engineers who are putting in little if-then statements that says like, well, if the applicant is female, then do this, otherwise do that. The problem was really with the principles of machine learning and the single-minded focus on optimizing for predictive accuracy. So, once I realized that, I thought, this is simple. We just need to write down what we want more carefully and constrain the process. But then when I started talking to people who have much more experience in, for instance, applications like criminal justice or surveillance or the like, I came to realize that to really understand the downstream consequences of a lot of the decisions that are made by the models and algorithms that we developed, it really does help to have people who have a very different view, for instance, of policing and surveillance than somebody like me might have, and to have people who've experienced it in a completely different way and can describe just consequences to you that you might not think about if you were just thinking about the problem abstractly.
These things affect humans, and I particularly care about the people that I interact with, and I especially think about my family who isn't going to have access to some of the things that I've had access to. I'm from a very rural city in Georgia, or Thompson, Georgia is very small, and I think that some of the implications of this technology might end up affecting my family. So that's kind of where I'm starting to see evidence of bias in these particular models, not even from a technical standpoint, but just from an application standpoint of this sucks. I can literally see how this is affecting people who look like me, and I wouldn't want to be in a scenario where this affects me.
Somewhat because of personal experience, I think that just again, being Black in America exposes you to certain types of experiences, and I think that when you've just dealt with those things firsthand, and yeah, when that's been your personal experience, I think that naturally is going to incentivize you to care about certain things. Like just having representative data sets, for example, is a great place to start, which I think is something that's very actionable and possible.
It matters for our discipline in that what we do is important. What we do is pivotal. What we do shapes our society, and we need to make sure that we're getting the best people. And I'm going to stand up and say I don't believe a field that is substantially underrepresented for over 70% of our population is a field that is necessarily going to be getting all of our best talent. So it's a lack of opportunity for our discipline. But then it's also the issue of it's a lack of opportunity for the people that are involved. The work that people in computing do, people in computing careers do, is important. It really shapes how we work, how we play, how our society operates. Heck, it shapes, some of our options in terms of our political system. It's really important. And like not allowing such a large percentage of our population to have opportunities to shape our discipline and to shape what's happening in computing, but in AI and machine learning in particular, is really a big loss for all of those people. So you can't just say, well, yeah, they'll find jobs in something else.
I think that it makes whatever you're working on more robust. And by having these different perspectives, you're allowed, or it enables you again to consider things that you wouldn't necessarily consider. So maybe that makes it harder in the sense that maybe you end up having to do more work than you thought you would have to do. But in the end, it ends up making a better algorithm or system or whatever whatever technology you're making. I think that it allows it to be useful for everyone.
Right? I'm building a bridge. Everyone walks that bridge. So everyone has to be thought about, not just, well, we're in New York, so I'm only going to think about the people on Wall Street. We don't do that.
I think that perhaps showing an agent how to do something is going to incorporate more bias because we might do things in a certain way. We might decide that some actions are more important than others. Some environments are more important to collect data in. I think that the way that you avoid having a bias in these systems or try to reduce it, I guess, is just to get a larger sample of people from different backgrounds, different environments that can show an agent how to do things, or maybe we can combine their different preferences in a way to try to be, I guess, more representative of where these systems would actually be used.
We want broadening participation to be an accepted and expected part of research. That means that has to be something that departments pay attention to, that they have to give people credit for taking the time to consider these kind of issues. And it's something that NeurIPS and conferences and similar conferences need to consider when they're thinking about who's thinking about everyone's broader impact statements and the work that people are doing. We're not going to solve this by just like convincing people things are good. We also have to change the environments and make them more inclusive. So that requires listening. That requires getting the right voices in the room and listening to those voices. So it's not merely enough. This is not just a situation where we need better advertisements. We need better reality as well.
Okay, this is good, but I noticed something.
Really? What?
So isn't this whole A Christmas Carol thing supposed to end with me begging you to know if we can prevent a horrible future? We're really getting off script here.
Well, I mean, honestly, I prefer something a little bit more optimistic. You've seen the future, and I hope, like me, you think it's going to be okay.
I'm all right with that.
So thank you, everyone, for listening to that. I appreciate it. I hope you got something out of it. But let's take a moment to reflect. So what have we learned?
I know.
Hey, how'd you do that?
Magic. Now, what have we learned?
Okay, wait a minute. That's my line. So what have we learned?
It's important for us to pay attention to the whole learning pipeline. There are interesting technical problems to be solved. There are moral concerns about what happens to real people's lives if we get this wrong.
And because it matters, taking the long view is essential.
Bias stems from the decisions we make. It's unavoidable. But we can identify it and quantify it and be cognizant of it. We can mitigate the damage bias causes by working in diverse teams and paying attention to how the systems might be used or misused, how they might be perceived or even abused to hurt others.
That's right. But we've also learned techniques. We've learned a bunch of them that are out there in the real world that show some promise for helping us to mitigate these issues. Also, there are ways of thinking from software engineering, from theory, even from programming languages that can help us.
Yes. Lots of stuff to learn, lots of things we can still do.
That's right. And we go back to something you said earlier, Michael, about whether any of this changes your original stance. Well, the thing is, where you started wasn't exactly wrong. To make basic progress, you have to focus on the things we've been focusing on as a community for decades. Focusing on the small is fundamental to getting things going. But the point of doing all of that was to prepare us for this moment when our research found its way into, well, everything and started affecting everyone.
Yeah. We said that what we were doing would be important someday. Who would have thought we'd actually be right?
Well, it turns out it's important and useful and powerful. And as you know, with great power comes...
high electric bills.
Yes, that. But if we do this right, machine learning will not only thrive as a field, but we'll all reap the benefits of the software that we write.
Code bless us, everyone.
Right. Well, thank you, Michael, for listening and for talking. And thank you for listening.